Hello, everyone. Welcome back to our mini lecture. Previously, we explored the basics of MCUs and learned that an MCU is essentially a highly integrated microcomputer. By programming it and connecting external input-output devices, an MCU can perform automated control and other functions. In this lesson, we will continue learning how to identify the model of an MCU, understand the functions of each pin, and delve into the minimum system required to make an MCU operate normally. Currently, there are many MCU models available, including 8051, PIC, MSP430, among others. The 8051 series is the most widely used traditional model. Let's begin by learning how to read the information on an MCU chip based on its model label. We'll use the AT89S52-24PC chip from Atmel Corporation as an example. The model consists of three parts: prefix, model number, and suffix. At prefix indicates that the chip is manufactured by Atmel Corporation. 89S52 model number includes the 89S series, 89 series, and 89LV series. Among them, 8 indicates that the chip is based on the 8052 core. 9 indicates that the chip has an internal flash memory. S indicates that the chip contains flash memory with serial downloading capability, meaning it supports ISP, in-system programming. C indicates that the device is a CMOS product. LV indicates that the chip is a low-voltage product, typically powered by 3.3 volts. 5 is a fixed value. 2 indicates that the chip has 8 kilobytes of internal program memory. The size of the program memory determines how much executable code can be stored in a chip. Generally, the larger the program memory, the higher the chip's cost. In actual use, you should choose a chip that suits the amount of functional code needed. Finally, the 24PC suffix can be checked in accordance with the table to find out the additional information it contains. From this, we can infer that at 89S52-24PC is an MCU produced by Atmel Corporation. It features flash memory with serial downloading capability, operates at a speed of 24 MHz, and is packaged in a plastic dual inline package, PDIP. This MCU is classified as a commercial product and is manufactured using standard processes. Next, let's take a look at the DIP pin diagram of the AT89S52 MCU. When reading the pins, face the side of the MCU with the label information, with the marker facing up, and count the pins counterclockwise starting from the first pin on the left side of the marker. The information in parentheses next to the pins indicates the multiplexing functions of the pins, which can address the needs of MCUs with a limited number of pins that still require multiple functions. The 40 pins are typically divided into 3 main categories. 1. Power and clock pins. Pin 40. Power supply pin, typically plus 5V for standard voltage and plus 3.3V for low voltage. Pin 20. Ground pin. Pins 18 and 19. External clock pins. When using an external clock oscillation method, TXAL1 is the input pin for the external clock signal, and TXAL2 is the output pin for the signal. When using the internal clock oscillation method, connect an external crystal oscillator, usually abbreviated as XO, and an oscillation capacitor, typically 30 picofarads, between the 2 pins. The internal clock oscillation method provides a more stable clock signal, so it is used more frequently. 2. I/O pins. Port 0. A bidirectional 8-bit tri-state I/O port, where each I/O pin can be controlled independently. The primary function is basic input-output. When using this group of I/O pins, it is necessary to connect an external pull-up resistor. Generally, a 10 kOhms pull-up resistor is used. The secondary function is to provide a data bus and lower 8-bit address bus for time sharing in an expanded system. Port 1. A quasi-bidirectional 8-bit I/O port with built-in pull-up resistors. Each I/O pin can be controlled independently. The primary function is basic input-output. This type of port output does not have a high impedance state, and the input cannot be latched. Therefore, it is not a true bidirectional I/O port. Before using this I/O port for input, a write-1 operation must be performed so that the MCU can correctly read external signals. In other words, a preparation process is required. This is why it is called a quasi-bidirectional I/O port. For the 52 series MCU, the secondary function of P1.0 is the external input for the T2 timer or counter, and the secondary function of P1.1 is the external control pin for T2. Port 2. A quasi-bidirectional 8-bit I/O port with built-in pull-up resistors. Each I/O pin can be controlled independently. The primary function is similar to that of port 1. The secondary function is to serve as the high-order address bus in system expansion. Port 3. A quasi-bidirectional 8-bit I/O port with built-in pull-up resistors. Each I/O pin can be controlled independently. The primary function is similar to that of port 1. When used for the secondary function, each pin is defined as shown in the table. Three. Programming control pins. Pin 9. A reset pin of the MCU. When a high level persists on this pin for more than 2 consecutive machine cycles, the MCU enters the reset mode and performs initialization. Pin 29. An external program store enable (PSEN) pin used to read data from external program memory (ROM) during execution. Pin 30. An address latch enable/program pulse input ALE/prog pin. After the MCU is powered on and operating normally, this pin continuously outputs positive pulse signals externally. The frequency is 1/6 of the oscillation frequency, and when the CPU accesses external program/data memory, it outputs a signal as a controller to latch the lower 8-bit address. The secondary function of this pin is as a programming pulse input when writing to the internal 8 KB flash ROM. Currently, this pin is not frequently used. Pin 31. An external ROM access control signal or internal flash ROM programming power input pin. When connected to a high level, the CPU reads from the internal ROM. When there is an external ROM expansion, the CPU automatically reads the external ROM after reading the internal ROM. When connected to a low level, it directly reads from the external ROM. During instruction execution, the CPU first accesses the program memory. The instruction code for the operation is fetched and stored in the instruction register. The instruction decoder decodes it, and the timing component generates a series of clock signals to complete the instruction execution. The temporal relationship between these clock control signals is the CPU's timing sequence. The MCU generates its timing sequence through the clock circuit. The 89S52 MCU has two ways to generate clock signals. 1. Internal oscillation mode. 2. External clock mode. To make the MCU operate normally, a basic circuit known as the minimum system must be constructed, as shown in the diagram below. First, the MCU needs to be powered by connecting the power supply and ground lines. Then, connect the crystal oscillator to form the clock circuit and the reset circuit. This completes the construction of the minimum system for the MCU. Let's summarize this lesson. We learned how to read the information on an MCU based on its labeling, introduce the pins of an MCU, including power and clock pins, I/O pins, and programming control pins, and discussed the three components needed to build the minimum system for an MCU: the power circuit, clock circuit, and reset circuit. Lastly, here is an assignment for you. Please select the specific model information of an MCU based on its model.